Thank you. So thank you for the organizer. So as Romain said, when I was invited as a speaker, I was at École Polytechnique, but now I'm a proud member of the Institut Langevin. So I will talk today about different point of view to understand localization. It's going to be quite different from all the talks that you have heard about during the week, because okay, first, there is no light. It was mostly quantum, so mostly scalar waves or complex waves. Second, I will have what I would call a modal point of view, meaning that I look at eigenfunctions, standing waves of the wave operator, and which means that the systems, most of the time, they are not open. They have boundaries. And eigenvalues are real, and as much as I can, I will avoid any propagation. Okay, it's a joint work with many people, so I will present many things, but it has been a development over more than 10 years, and it has involved many people. First, a mathematician, and the landscape has been developed with Svetlana Memboroda, who is currently at the University of Minnesota, moving to ETH. But now we have applications with many teams, among which I will mention a few from Institut Langevin as well. So I will start with the very basics, standing waves. So when you learn about standing waves at school, it's what you learn, basically. It's everything looks like this. This is in 1D. This is in many dimensions. So either they are in the continuous translation invariance in space, and you have plane waves, or you are block waves in the case of condensed matter physics. The thing is that when you look at the modal situation, and you look here, we'll immediately move to Schrödinger equation. You look at Schrödinger equation without potential, then of course you have this. These waves here, it's with the Neumann boundary condition, so the fundamental is flat. But any high-order waves, high-order eigenfunctions, is delocalized. You perturb a bit this, you put a bit of a bump in your potential. You don't change things too much. Essentially, they are a bit different, but they are all delocalized. The surprise comes when you, instead of adding a small bump, you add a potential which is a huge noise, and here immediately you have something drastically different, even for the fundamental modes, but also depending on dimensions for many or all high energy modes. And this, we have to take a minute here. Maybe it's obvious for the senior people, but for the youngest one in the audience, the shock that is this for even from the mathematical point of view, because when you have translational invariance, as I said, in classical mechanics, it means conservation of momentum. Translational invariance of the law of physics means conservation of momentum. The wave counterpart of conservation of momentum is the fact that your Hamiltonian or your operator, your wave operator, commutes with the generator of the translation group, which means that basically you can find your eigenfunctions as eigenfunctions of the generator of the translation group, which is the momentum operator. So you can find eigenfunctions as eigenfunctions of the momentum operator, so plane waves. If you have a discrete translational invariance, you have the block waves. So basically, translation invariance means no localization, plane wave. Here, you have something that looks very much like translational invariant. In fact, from the random point of view, it's statistically translational invariance. The law is translational invariant. And yet, immediately, you have no localization, no delocalization. So this is striking. This was a real surprise. And you have to understand that, Although, of course, if you understand this as scatterers and you have a very dense scatterers and you have the waves that are going in circles, sort of, which is the propagating way of looking at Anderson localization, of course it works. But it works also because a bit further than that, you have something that looks the same, but it's not exactly the same. If you would take this pattern and repeat it periodically, then you would break down Anderson localization. Although it looks very disordered, it needs the fact that at long range, sort of, you don't find exactly the same. Probabilistically, it's the same, but it's not exactly the same. So you have this destructive to ensure destructive interference at all scales. So this was a surprise. So everybody says, okay, so that was heard before. You have to have the picture of Anderson next to the picture of his paper. The difference is that this picture I took myself. It was at a 100 event of the Rutgers, the Statistical Physics Conference in 2008. And I remember vividly the talk of Anderson. Anderson started by talking about Einstein and diffusion for about 2 minutes. And after 2 minutes, sort of he got bored. He said, okay, enough spoken of Einstein. Let's speak about me. That's Anderson. So he's very famous for, so here I've put a few important review papers. And here is one of the landmark. It was, although it was, presented by Anderson in '58, it was very difficult to find actual Anderson, to prove actual Anderson localization in real life, in real physical system. That is one of the observation in cold atoms, the landmark experiment performed in Alain Aspec's team at Institut d'Optique, where you have a localization in a one-dimensional disorder of an initial Bose-Einstein condensate that starts expanding, and sort of a part of the Bose-Einstein condensate is blocked is frozen in this localized state. So for us, for most of the talk, Anderson localization will be about this operator. So this is the discrete way of. Sometimes I will use the continuous description. Sometimes I will use the discrete one. So basically, you have something like this that will become the Laplacian in the continuous setting, and you have a potential, and you can shift the potential by a constant value. Usually, when you are in the tight binding model, you have this T is set equals to 1, so it's everything is in the strength of the potential here, and the potential is taken symmetric between minus W over 2 and W over 2. And the type of diagram that you have in 3D, for example, so this is 3D on a cubic lattice, is that you plot, so here is the disorder strength, is the W here. In fact, it's W over T, you assume that T equals 1. And you look at whether, this is on the horizontal axis, you have the energy. And so for every given strength of the disorder, you look what is localized or delocalized in the eigenfunction. So the spectrum is between -6 and +6 for W equals 0, because it's the spectrum of the Laplacian, tight binding Laplacian in 3D. And if you add a potential that varies between minus W over 2 and plus W over 2, you have a spectrum that is between -6 minus W over 2 and +6 plus W over 2. So something that a spectrum that is here. And what numerically can be shown is that you have sort of this phase diagram, which means that for a small enough disorder, so the difference between these two graphs represents the same thing. The difference is the method of calculation. So here the transition was computed either by a transfer matrix methods or multifractal analysis. And here it's more recent, so it's more fancy. So the authors, they used the neural network, and they taught the neural network to recognize what is a localized or a delocalized eigenfunction, and then they ran it on a large number of random seeds. So the diagram that you have here is that at low enough disorder, the spectrum, essentially, you have delocalized eigenfunction in the center, and on the edge here, on this edge, you have localized eigenfunction. And as you grow, the disorder strength grows, you have more and more of this part of delocalized eigenfunctions, which goes between, so here it's it goes like this, you know, plus 6 plus W over 2, like this. And this, there is a region here of more and more localized eigenfunctions, up to a certain value, critical value of the disorder strength, for which everything becomes localized. So, so this is the something that is, say this is from the totally model point of view, but if you look, very often the explanation on Anderson localization is given in terms of propagation. So you have this propagation, and this is what you have heard, this, the type of vision of Anderson localization, where you have propagating wave in the medium full of scatterers, and sort of the scatterer made the waves to go in circles, and more, and if the scatterers are dense enough, or disorder is strong enough, then sort of they cannot escape this loop, and they become localized. So, and there is this separation between these modes that are localized at low energy and the eigenfunctions, or the modes that are diffusive at large energy. The transition is called the mobility edge. So over the years, for example, so this mobility edge exists in 3D. I will come back to what happens in the lower dimension. But in 3D, you have so this transition, and below you are localized. So what happens when you go next to the localization threshold, which is the mobility edge, the localization length diverges with the power law. And when you are above the mobility edge, you have conducting states, so you can assess the conductance of your system, and the conductance of the system, or the conductivity of your system, decreases when you go near the mobility edge, with also a power law. And these are known relations. When I say known, it means in physics, because I've been working for 10 and 15 years with mathematicians, and I've learned that there is a very big difference between to know in physics and to know in mathematics. So everything that I'm speaking about here in physics, I will tell you about what is known in mathematics. So there is this very famous paper also that was mentioned earlier in the week, which is, so I want to simply draw your attention to the date, you know, 79. So it's usually when you have a talk about Anderson localization, first you have the paper of Anderson in 58, then very quickly you have this one. So very quickly, but you have to imagine, it's 21 years later. So 21 years later to wait for something that is significant in terms of a result on the understanding of that. So, and this is the very famous paper where the authors look at the dimensionless conductance, and so, and the spirit of the paper is that what matters, you're going to have samples where the conductance will be the important quantity to look at, and not the conductivity. And the conductance will depend on the size of the sample. And the idea of the authors is that you do scalings with that. And sort of it means that if you have a conductance of a sample of size L, then you can sort of build and understand the conductance of the sample of size 2L by just gluing and making simple rules about computing the conductance of serial and parallel conductors. So the conductance of there is a dimensionless conductance where you take the conductance, and in fact you divide it by the natural quantity, dimension quantity, which is E squared over 2h bar. And this quantity, when you have a sample of conductivity, homogeneous conductivity sigma, this is very simple math, it scales like L to the d minus 2. If you are in 3D, you have a conductance that scales like the length of your sample. You know, and the resistivity, the rho L over S, you have a L over L squared. It's 1 over L. So this is this one. So in D dimension, you have a L to the d minus 2. And the whole idea here, which is striking, is that saying that in fact the way the conductance will grow when you change the size of the sample will not strictly depend on the size of the sample, but will depend mostly on the conductance itself. So there is a parameter beta which is how you change the conductance when you change the size, but saying that this beta depends in fact not on L but on G. And once you have done that, and you have assumed that you have a beta of G, then you can draw this thing, because you know that for very large sample or very large G, what you're going to have is behavior that are like d L to the d minus 2. And if you put L to the d minus 2 here, you obtain beta equal d minus 2. So you know that you have this asymptote at large G. And at small g, you have this very simple and crude, it's papers before, it seems it was easier to write, you say simply, for small g, exponential localization is surely valid. And therefore, g folds off exponentially, and that's enough. And that you have this, and in between, you do continuous line, and you say, okay, I do continuous line and with a continuous asymptote, and I don't draw that. I don't draw that I will go to 0 in a finite value of g. The solid circle, this unphysical behavior necessity is shown dashed. So this is called inphysical, so it's ruled out. So it's much simpler. Okay, math. Math is a very different story. It took a very long time for mathematicians to figure out what to do with Anderson localization. And in fact, the results are surprising, because, okay, in 1980, you obtained a localization in 1D for random potential with IID variables. And in fact, in 1D, everything is understood, mostly, because you have the very nice tool of transfer matrix. And with transfer matrix, you can compute Lyapunov exponent, you can compute everything. So both in physics and in math, 1D is covered, essentially, except for the basic Anderson model. You can have more complicated things if you have nonlinear Schrödinger equation or interacting particle. But for the basic 1D type binding, it's okay. In higher dimension, what was proved in 1983 by Filoche and Spencer is that you have always localization in the type binding model. So it means there always exists at least one localized eigenfunction. And even more recently, in 2001, the method that was based on which was based this result was quite difficult, the multi-scale analysis. And there was an easier method that was a more elegant method that was formed more recently in 2001. What is amazing is that mathematicians are not able to prove that there is delocalization. So the thing that you have to understand, that the thing that physicists say every day, what is difficult to do in the lab is to have localization. Delocalization is everywhere. This is precisely what mathematicians cannot prove. They cannot prove that there is delocalization, at least at small disorder. They can prove that at large disorder in the tight binding Anderson model, you have localization. So localization seems not to be too much of a problem. There are always localization, and for strong enough disorder, you have the localization. Delocalization is a problem. And so if you are not able to prove that delocalization exists, you are not even able to prove that mobility age exists, or Anderson transition for the matter. So that's the dialogue between physicists and mathematicians is very interesting for that. Okay. So what I'm going to show you today is a different approach from what has been done for a long time. Because initially, when you speak about quantum physics and mathematics, immediately the first things to say is quantum physics is algebra. It's matters of operators, of Hilbert space, of commutation. And then when you look at localization property, you are looking at the spatial structure of eigenfunctions. And eigenfunctions are solutions to a PDE with an elliptic operator. So you move to the field of analysis. So it's more the field of analysis. But then when you say that the potential is a random object, then you move from analysis to probability. So for a long time, it has been the toy of probabilists. And even in physics, all the improvement and all what has been done in Anderson localization has been done on the base that it's probability. And there must be something that can be drawn from the probability. I won't have the time, of course, to make a full review of Anderson localization. But the point here that I want to stress is that most of the things that have been accomplished so far is by looking at the object from the beginning as a probabilistic object. What I'm going to show you and hope to convince you today is that there is a machinery inside that has nothing to do with probability, that can be applied to a single realization with no averaging, can be applied to deterministic system, can be even applied in some case to periodic systems, to something that has nothing to do with localization, and that this is a sort of it's not opposed to what have been done before. It's more like perpendicular. So because there are still a lot of open questions about Anderson localization, about very simple Anderson localization. So I've spoken about tight binding models. I will speak also about continuous model. In the case we have a continuous model, very often I will talk about this type of disorder because we are working with cold atom people, with the team of Alain Aspect at Institut d'Optique. And the type of potential that, disordered potential that we use in the continuous model is this one. So it's the potential that is described with the probability of having an excursion of size v, which is exponential, and with the correlations that are essentially Gaussian. And you very usually, we will see this parameter very in the future in the talk. You have this parameter, which is the parameter eta, which is basically the ratio between the height of the bumps, the height of the potential, and the correlation length, so the correlation energy. So this means that eta equals 1 means very large excursion of potential, so you're going to have very deep wells, and we are going to be in the semi-classical regime. And eta goes to 0, means very shallow wells with most likely eigenfunctions and fundamental states that will spread across several wells, and then we'll go to the quantum regime. So an eta equals 1 is the transition. So we'll find this later. Okay, I'm going to introduce you to something that we have been developing for the past 10 years now, which is the localization landscape. So the localization landscape, the definition is absolutely very simple to get. So you'd start from I will start from in the continuous setting. You take an Hamiltonian with positive eigenvalue. So if not, you shift a V up by a constant so that you have positive eigenvalue. You compute the time-dependent Schrödinger equation. So you solve this and you compute the eigenvalues, the eigenfunctions. And for the potential, you will take something that looks like the random potential. In this case, you take something on a chessboard and you assign random values on each cells of your chessboard, random values between 0 and a value Vmax, uniformly distributed. So if you compute that on this example, you look at the first 5 eigenstates, they are Anderson localized with exponential decay, like this, even on the localization landscape equation looks very much like the time-dependent Schrödinger equation. So instead of putting ipsi here, you put 1. So if you do that, so far it looks like it has no meaning at all. So if you do that, what you get as a function is a function that is positive because the spectrum of this is this object is positive. So it looks like a positive function, a series of bumps like this, series of bumps. And you can separate, in fact, these bumps, they separate, they partition the domain into small regions. And, and these small regions, the partition is shown here in red lines. This is in 2D. If this were in 3D, you would have a 3D localization landscape, and the partition region, the valley, will be hypersurface, like separating, like a foam separating the regions. And the thing is that, you can see that already immediately here, is that each of the first 5 eigenstates seems to occupy one of the region. And I will show you, try to convince you that this object, although it's very simple to compute, very simple to define, bears a lot of information about many things, spectral and spatial information about the eigenfunctions. Okay, this is part of a project, a big project now that we have that has been funded by the Simons Foundation. So, what is very interesting in this project is that you have 5 mathematicians. They are here, and Doug Arnold. So, Dominique Copin, we got him into the project last year, and this year he got the Fields Medal. So that was not so bad. Claude Weisbusch is the one that you have heard about the polaritone this week. So he was the one who discovered the strong coupling in semiconductors. So this will be an ongoing project, and that's why I'm going to talk a bit about math, and you will see some math, because the way we go is really to try to assert and to have strong results that are sure. And it's very interesting when you, so from the sociological point of view, when you see the debate on Anderson localization, they are fierce, they are very heated sometimes. And with theoreticians, physicists, theoretical physicists, they are sometimes very heated. I discovered that bringing a mathematician with you is like bringing your big brother at a school fight. You know, the guy says, "Oh, it's wrong." Yeah, but we proved it. And then end of the discussion. So there's nothing that a theoretical physicist doesn't respect anything but a mathematician. So that's okay. So enough with the sociology. So if you start, why is this landscape interesting in the first place? The first property that you can have with the easy to derive is you start from the eigenfunction equation, the steady-state eigenfunction equation, and you invert it by introduce the Green function, the zero energy Green function. So you write the inverse of the Hamiltonian in this kernel form, and when you do that, you can simply E is positive. You can take the amplitude at any point of the wave. You have this quantity, but you exit this quantity by taking this supremum, and you are left with this. So there is something that is quite surprising, is that for all eigenfunctions normalize L infinity, which means divided by their supremum. They satisfy this quantity. They sort of are controlled by the same object. Although it's not obvious, but the amplitude is everywhere, or you have the E factor here, but it's everywhere controlled by the same object. Not only that, but in the case of a second order operator, second order differential operator, as is the Hamiltonian for quantum physics, the Green's functions are positive. So you can remove the absolute value, and you get U is the integral of the Green's function at zero energy. And when you do that, this is simply the solution to HU equals 1. So that's basically the scheme. You take the localization landscape, you look at, from above, at the localization landscape, you look at the valleys. What are the valleys? It's the location, the place where U is small. And when U is small, sort of it's going to constrain the eigenfunctions, and even more the low energy eigenfunctions, to be small, to have small amplitude. So sort of these are the regions where it's very difficult for the eigenfunctions to oscillate with a large amplitude. And this is what we see here. But this was the first time we discovered the landscape was by doing this. But in fact, came later something much more important and much more revealing, is that when you make a change of variables, instead of the eigenfunctions, you take another variable, just dividing the eigenfunctions by the landscape, which is a positive definite eigenfunction function, so it's perfectly okay, it's perfectly safe. If you make this change of variable, it amounts to what the operation of conjugation of the Hamiltonian, so multiplying by U on one side and by 1 over U on the other side. you transform the equation, the Schrödinger equation, into a new equation, which looks very much like a Schrödinger-like equation, except that here you have something that looks like a metric. And here you have the potential V has disappeared, has been replaced by 1 over U. So 1 over U looks like it acts as an effective potential. And indeed, it acts as an effective potential because you can prove mathematically the following identity, which is the energy of any state, which is usually the sum of the kinetic and the potential energy, can be rewritten as the sum of a reduced kinetic energy and an effective potential energy, where the price to pay is that here you use phi instead of psi. The scalar product that you use is a scalar product that has the weight u square here. So phi is u square normalized. And here you have simply the average value of 1 over u. So this tells you that the energy of any state cannot be smaller than the potential energy predicted by 1 over u. So 1 over u acts really as an effective potential. So it means that what I showed you, that the localization landscape looks at this series of bumps. If you think of 1 over u, it's the reverse. So what's going to be 1 over u? It's going to be a series of basins. And what are these lines, these valley lines, that are the lines of minimum of u? For 1 over u, it's like crest lines. So it's like, if you look at the potential, it's like you have a series of basins separated by barriers. So that's, and it has a quantum explanation. So now you look at the first eigenstate, and you superimpose with the drawing of the barriers, and you see that they fit perfectly here. And when you do, you look at the, we're going to look at the large number of modes, and we're going to remove each time, we're going to remove the lines where 1 over u is smaller than e. Because it means that sort of we are increasing the energy of the eigenfunctions, and like in any normal potential, we are flooding at level E to see really what is the confining power of the potential. We are looking at energy. So if we do that, see, if you, without the lines here drawn, you would think that the eigenfunctions, they pop up at random. But in fact, they don't pop up at random at all. They are absolutely controlled by this pattern, in the underlying pattern. They all see it. Independently of where they are localized, they know, they feel it, sort of. And as you increase the energy, what happens is that you start sort of flooding the potential, you open regions, and you start to have some kind of delocalization, because they can extend, or the region merges, and you can have more delocalized wave. Although you have some regions that stay for a long time, and you're going to have an eigenfunction that's going to be localized somewhere here or here, see, because the eigenfunctions, so they occupy at the end all the domain. So I think that we have enough of it. So, how can we understand this landscape? This landscape, I call it the tribe of fundamental. Why? Because if you look at this, it looks like a series of bumps. We have seen that this bump corresponds, roughly speaking, to a basin. It's even more than that. Each of these bumps looks like the fundamental mode of the local region. Why so? You take U and you make a linear decomposition on the basis of eigenfunctions. You have the right to do that. Eigenfunctions are a basis. If you do that and you look at the decomposition, the coefficient of the decomposition here is very easy to compute by simply applying H and using the hermiticity of H. And you can very easily derive that the coefficient here, in fact, is the scalar product of psi with 1, so it's the integral of psi, divided by its energy. And here you pause here and you look at a point x and you say, I'm at a point x. You have the value of u. What in this sum contributes to this value of u? Here you have a sum of all eigenfunctions. So you have choices. Either psi is a localized state far from x, which means that this is very small. It doesn't contribute to the sum. Or it's a localized state around x, but it's not the local fundamental. Hence, that will be something that will be oscillating with plus or minus. So this will be small, and this will be larger. Or it's a delocalized state, in which case it's going to look very much like a plane wave, and this quantity will be very small, and this will be very large. In short, there is one main, for each point x, almost all, in all cases, there is one main contributor in this sum, and one only, which is the local fundamental at point x. So this is basically a weighted sum of all local fundamentals. It displays you immediately where are the fundamentals and how big they are. So this is the first thing. Okay, but you can use this. You plug this back into the energy that I've shown you before. So you say, okay, here is the one. This is a 1D example. You have the U, the landscape. You look at the first four fundamentals, first four eigenfunctions, and you see that they fit perfectly in each of the bump. But if you say that locally the eigenfunctions look like the landscape, and you plug this in this formula of the energy, the one that I showed you before, you know, the grade phi with a U square norm, then this part almost disappears. Because the gradient of psi over u, if psi is proportional to u, gradient of psi over u disappear. And only this terms remains. And this terms is here, and it's something that looks like this, and it can be almost approximated with a parabola. And we have this very simple approximate formula, which tells you that you look, not only you have where the eigenfunctions are, the fundamental, but the height gives you the energy immediately, an approximation of the energy. So these are simulations made in 1D. When you have this factor 1 plus d over 4, d is the dimension, and so these are 1D simulations. Each realization, you take the first eigenvalue, the 10th eigenvalue, the 25th eigenvalue, and you change the realization. So these are for very different realizations. So the value of the fundamental energy changes a lot, but what doesn't change is the fact that each time it changes, it's followed by the value of 1 over u in the well. In 2D, it's the same. It's instead of 1.25, it's 1.5. And let's take an example, very simple example. You take the fundamental, the well, one well, simply. So you know everything. You know the eigenfunctions. You know the energy. They are proportional to n square. You know the fundamental, which is pi square over a square. Let's compute the landscape here. What is the landscape? Is the solution to, there is no potential, v equals 0. The Hamiltonian is minus Laplace. In 1D, it's minus u square, minus second derivative of u equals 1. The solutions to that is x times a minus x over 2. So the landscape is a parabola that vanishes at both sides, at both ends of the well. 1 over u is this object, is this effective potential. Now you compute what is the value, so you have one basin here. You compute the energy by saying, okay, what's the minimum of 1 over u? It's at the center. It's 8 over a square. And if you compute this quantity, the integral of x, a minus x, integral of u over integral of your u square, you obtain 10 over a square, which is 1 plus d over 4, 1.25, the value of the minimum at the minimum of 1 over u. And this is the approximation, the predicted approximation from the landscape to the fundamental energy. So 10 over a square is the prediction, and the actual value is pi square over a square. And actually what's very interesting to look at is the energy distribution of the fundamental state. You take the fundamental state. Normally, if you are in quantum physics, this V is 0 here. And all the energy is kinetic energy. Now, if you look at the new distribution here, all the kinetic energy has been almost transferred into potential energy. What it means is that the energy of this object, the fundamental of a well, is understood now as a classical object. It's as if you would have a distribution of mass here, according to psi square, but lying on a potential. So you have transformed all the energy of the fundamental eigenfunctions from kinetic to potential. You have made out of all the fundamentals of your system, you have made classical object of them. And even for the higher energy eigenfunctions, a part of their energy has been transferred by this game into potential energy. Whereas all these eigenfunctions, they have zero potential energy in the normal decomposition of the energy, the usual one. They have now something that looks like a potential energy. And the fundamental is almost a classical object. So, and this is a very important take-home message. It means with the landscape, with this transformation, you can look at your system, you have the right semi-classical first order. And even for a quantum system. And for example, you take something much more complicated, the correlated potential. You have this effective potential here that is very complicated, lots of basins everywhere. You look, this is computational, you look at the energy, you look at the minima of 1 over u, and you compute the ratio between the minima of 1 over u and the eigenvalue, the energies. And you see for the first 150 energies, it's almost 1.5. So you compute one landscape, immediately you have in one picture, you have all the basins. You know what are the shapes of the eigenfunctions in all the basins, and you have the estimate of the energy within a few percent. That's okay, now that you are skilled in the landscape, you're going to play. So you have here a potential that we're going to put in the Schrödinger equation. So the game is to say where is the fundamental state here. So if you want to play, so you know that in quantum physics you would look for a deep well wide enough. So somewhere here or there are a few contenders here. Okay. But with the localization landscape, you say, okay, we compute the landscape, we compute 1 over u. 1 over u is here. And now we look at where are the deep states. Here, there, and somewhere maybe here. So these are the prediction of the 1 over u. You look at the computation of the actual eigenfunctions, and they fall exactly in the right order within these wells. Now, we change the game a little bit. This is a new potential. So this is a new potential. It looks like the same but the difference is that instead of going between 0 and 4, it goes between 0 and 256. So you have changed the height. Here, it seems that it's very difficult to see a difference from the naked eye between this and that to predict the eigenfunctions. You compute the effective potential. The effective potential by the landscape is very different. Why is it very different? Because it solves the equation of the Hamiltonian. So it has also the Laplacian part. So where the original potential knows only the value of the potential at a given point, it's what your eyes sees. When solving the landscape equation, you are sort of integrating the knowledge about the connectivity with the Laplacian. So you are integrating the connectivity, the local connectivity of your environment. And you're bringing it and you are transforming it into a new potential. So you are renormalizing the disorder by doing so. Okay, this has been so one of the first experimental realization of this has been done at the Institut Langevin within the team with Patrick Seba and Michael Atlan. And in fact, because solving HU equals 1 doesn't mean anything in quantum physics. You know, there is no HU equals 1 to solve in quantum physics that I know of. But with plates, vibrating plates, putting 1 on the right-hand side, it means applying a constant pressure, uniform pressure on the right-hand side. How do you apply an uniform pressure? By simply you seal the back of the plate and you depressurize. And so the atmospheric pressure for you is applying a uniform pressure. So it's putting the 1 on the right-hand side for you. So that was done. So you take a plate. The system, the vibrating system, is a plate here. The plate with some kind of clamp points, and you depressurize, and you can observe the landscape. These are nanometer deformations of the plate, and this is the first picture of a localization landscape ever. It was done at Institut Langevin. And you compare this. So when you have this is a static deformation. From this static deformation, you can predict where you're going to have localization, and the height of the bumps, they tell you at which frequency you're going to localize. And this is the comparison between the frequency of the waves that was and the maximum displacement, and this is the red curve is the prediction by the landscape. And these are the points obtained by measurements and numerical simulations, so which are here. So it means that with a static measurement at 0 frequency, you have information on how it's going to vibrate your structure, at least at low energy. And not only that, but we used it. You can use it because now you have something that can be used as a design tool, an engineering tool. Because if you say, for example, this was a game that we played with the interns that we had at the time. It was a small project. Let's say you have a plate like this and you want to isolate a region, mechanically isolate a region from another. But to do that, you cannot just put barriers. You have just pins that you can clamp. You can clamp individual points. And you have a fixed number of individual points that you can clamp in your plate. Where do you put your pins so that you have maximal isolation between this part and this part? This is a complicated problem to formalize in terms of spectral vibrations. But with the landscape, you say, okay, if things were ideal, the landscape will vanish here. So you solve the landscape equation, the ideal landscape equation, by solving this and putting vanishing boundary condition here. You obtain an ideal landscape. And then you have your pins here, and you can move them. And for each configuration of pins, you have a landscape. And the design tools tells you, okay, and you have even a natural norm, a natural distance between two landscapes that is given by the bilinear form of the wave operator, which is the energy. So you have a criterion to say how close you are from the ideal insulations. And okay, this is the optimal solutions, for example, for 16 pins. And some things are okay. Of course, they are positioned not on this boundary, but it's not obvious where to put them a priori. And when you do that, and these were the results of simulations, and these were the experiments, and you have to realize that it's vibration of thin plates. So we are working with the Bally-Laplacian. So Bally-Laplacian is a very rigid operator, means that it's very sensitive. You move two pins by a very small amount, you change a lot the leakage and the insulation. So it's a very sensitive business. And this is the movie of the vibration depending on the frequency. And you see that there is a bit of illumination here, but it's a problem of the camera. But you see you see that for a long time, the only part that is vibrating is the central part. And in fact, if you put a vibration pod, the vibration source outside of the X, you have very limited vibrations for a long time. So you have strong insulation between the two regions. So this can be used as the design tool. So not only have we have this view of the fundamental states, and we know where they are, but there is something that is even stronger than that, is that we can look at the exponential decay at the exponential scale. And the reason for that is that we have a tool, a mathematical tool that I didn't know about before, which is the equivalent. Everybody has learned about in quantum physics about the exponential decay through a barrier when you have a wave inside a quantum well. There is, in fact, a tool, a mathematical tool, which works for any potential in any dimension, telling you what will be the exponential decay of a wave function outside its well. And this tool is the Diamond distance. So this is the distance that you can define for any potential at any energy. This is the positive part. And this object is a local metric. And this local metric, you can use it to build a distance. So the distance between any 2 points of your domain is the infimum of all paths going from one object to another of this quantity. And this quantity is controlling the decay of the eigenfunctions outside its existent well, inside the barrier. So if you do that in 1D, what you get is simply the decay, the exponential decay of the tunneling effect in 1D. But in any dimension, it says simply that, okay, to assess the value of the eigenfunction somewhere in the barrier, you have to probe all the possible paths and minimize this, and this is a control of the exponential decay. So in many cases, for V, which is random, this doesn't work as a very good tool in higher dimension, because you have very often paths where V will be very small, and this won't be a very good control function. What we have changed is that we have changed, when replacing V here by 1/u, in fact, we have shown that we can predict the exponential decay of the eigenfunctions outside their existence region. And here, this is an example at the linear scale. You have an eigenfunction here. Here you have all the regions. You think that here the eigenfunctions has almost vanished. But if you look at these eigenfunctions at the log scale, you realize that in fact, even at the very tiny scales, it follows the pattern of these walls and barriers and basins. And that we can predict, here it's a 10 to the minus 10 decay. We can predict the exponential decay of the waves using this tool, but replacing V by 1/u. So this is the mathematical. I told you that I would show some mathematics. This is the mathematical explanation. So how do you say that something decays exponentially in mathematics? It's here. So instead of saying psi goes like exponential minus this, you say integral over the domain of the energy of the waves times an exponentially growing weight is controlled by the energy of the wave, which means that in order for this to remain finite, this has to decay to compensate for the growth of this. So it means that this decay like this. So it's how you express. So it's quite difficult to read when you read the mathematical papers, but it means simply that. So an example, for instance, here you have a 2D potential, binary Anderson model, which means that the potential is either 0 and 1. And the probability to have 0 is 0.6, which means you're in 2D, you are above the percolation threshold, which means that if you are on the white point here, if you are at 0 potential, you almost can escape to infinity with probability 1. So if you look at the distance, the Hagman distance here between any 2 points, it's almost 0, because it's degenerate everywhere. There is no distance here, there is no barrier. Almost any 2 points that are in the white region, they can be connected, and there is no distance between them. this is not the case at all for 1 over u, because the potential, the localization landscape, closes the barriers and makes a pattern that is very different. And here, for example, is the fundamental state, and here are the barriers predicted by the localization landscape. And what you see is that the exponential decay, this is at the exponential scale, you know. The exponential, this is 10 to the minus 8. At the exponential scale, the eigenfunctions knows where are the barriers. So you control very finely the exponential. So you have the decay. So you have the prediction of how behaves the eigenfunction inside the well, and you have the prediction with a different tool of how the eigenfunctions behave outside of the wells. So you can reconstruct, sort of by gluing the two, you can reconstruct. This is an original state computed by solving the Schrödinger equation. This is the reconstruction by the localization landscape. So the localization landscape is much faster to compute. So this is the type of prediction. So there is a lot of things about the spatial structure of the eigenfunctions that we know with this tool, that are in fact hidden in this object. But also, what's amazing is that you have prediction also on the spectral side. So the spectral side is the density of state. So density of state, we have seen already that with the localization landscape, you can predict things about the energy of the low-lying eigenfunctions. But at higher energy, what do you do? Can you predict the density of state or the integrated density of state? And there is a theorem, there is a tool that is very well known, is the asymptotic Weil law, that tells you in a system like this, at infinity, for large energy, how do you predict the integrated density of state, the counting function? Simply, you count the volume in phase space. You count the volume in phase space that is enclosed between a level set of H. So this is an actual theorem, but this works very badly at low energy. This comes essentially from the uncertainty principle. It's due essentially to the fact that any state in phase space, in any eigenfunction in space phase, will have a volume more or less equal to 1. And simply, you sort of overlap all the, you put together all the eigenstates, and you get, you change the counting of the number, counting the number of eigenstates into the counting of the volume in phase space. Now, if we replace, in this formula, we replace V by 1 over U. Here, you have 6 examples. Here are in 1D. So these are, for example, random potential with uniform law. This is random potential with Boolean law, 0 and 1. This is a random potential with correlation inside. And this is not even a random potential. It's a periodic potential. In green, you have the asymptotic Weil law that is known, that I've shown you before. In black, you have the actual computed IDOS, counting function. In red, you have the prediction by the localization landscape. So and what is amazing is that even in the periodic case, you have the correct prediction of where to start and the shape after. It means that it has nothing to do, really. It's a machinery that applies to anything, not even disordered, you know. So it's something that has to do with understanding what the waves really see as a potential, and which is not the initial potential that is put in the Schrödinger equation. Okay, I think for the sake of time, I'm going to skip this. There is another way of computing the density of state that actually has been proved, and it's but it's not a formula that gives an approximation. It's a formula that gives a bound between from above and below that we have shown, but this is a mathematical theorem that we can build a function from the localization landscape that can bound from above and below the actual IDOS from 0 to infinity for any type of potential. So you have something, so I won't enter the detail of how it's done, but it means that if you have, for example, this, you compute the counting function, the integrated density of state for an actual disordered potential, and you compute this function, which is built from the localization landscape. You can use it and shift it horizontally and vertically when you plot this in log-log scale, so that it sort of makes a band from above and below. The same function, so that you have asymptotic behavior at infinity and at 0 at the same time. And but I won't enter the detail of this. But this, and this is the last thing where we are now in sort of in theory, is to show that in fact with the localization landscape we came to realize that we understand how eigenfunctions are in phase space. That's the why we understand where eigenfunctions are in phase space, is because when you have this Weil asymptotic law that works by replacing V by 1 over U, what it means? It means that you can compute the number of eigenfunctions up to energy E by just computing the volume in phase space. If you are able to do that, it means that when you go from energy E to energy E plus dE, you go from one subset, one level set to another level set. Between the two level sets, you have increased from E to E plus delta E. It means that in this region that you have gained in phase space, you have found exactly the differential of the counting function, so that you have here the DOS. So somehow it means that with this subset, you know where are in phase space the eigenfunctions. What does it mean for an eigenfunction to be somewhere in phase space? What is the language for that? The language for that is the language of Wigner-Weil transform. So Wigner-Weil transform is a way of transforming the language of Hilbert space and eigenfunctions into operators into a language of phase space and complex valued function. So go from operators to function. It has, okay, these are the definition. You transform something like this into a function in phase space. So it can be P, but I use K here to avoid having all the H bar everywhere. And what is very important about this Wigner-Weil transform is that the Wigner function of a state, psi, is a quantity that looks very much like the probability density in phase space. Why so? You have the marginal integral along K, which is a probability density in X. The marginal integral in X, which is a probability density in K. Which means that this quantity, this Wigner function, is very often positive. And in fact, you have another property that is very important, is that the inner product of two Wigner functions is the square, with a multiplicative factor, is the square of the inner product of the eigenfunctions. Which means that two eigenstates, which are orthogonal, they have their Wigner function that are orthogonal. Since the Wigner function are almost positive everywhere, so mostly positive, it means that sort of, if you have two states that are orthogonal, their Wigner functions are non-overlapping. So they are separate in phase space. The inner product of any two Wigner functions is always positive. If you take psi2 to be a Gaussian of size 1, so it's going to be either in phase space something that is elongated in the k direction or elongated in the x direction or something more isotropic. Whatever you put against the Wigner function of your function psi1, it gives something positive. That means that first out at the size 1 in phase space, the Wigner function gives a positive contribution. So it can have negative excursion, but not too much. And most important, you can transport, instead of computing a mean in a quantum way by simply taking applying the operator of the observable to psi on both sides, you can simply compute the mean as if you were using the function, the Weil transform of the operator. So for example, if you're looking at the kinetic energy is h bar square k square over 2m. Instead of looking at this, you compute A of xk, which is h bar square k square over 2m, but you integrate it over the Wigner function of psi, and the Wigner function is seen as a weight in phase space, and it's the way you can compute the average kinetic energy of a state. So you can do that, and the fact that the Wigner the counting function with the landscape predicts so well the actual counting function means that in the region that I showed you, you have the support of the Wigner function at energy E. So it means that if you look at the Wigner function of in phase space, and even if you sum them up to energy E, you're going to obtain a function like this that will be integrated over phase space, that will be the IDOS, because the integral of any Wigner function equals 1. It's a probability distribution. It looks like a probability distribution. But if you say that essentially this function here is supported inside the level set at energy E, it means that you know where the wave functions are in phase space. You know that up to energy E, the wave function in phase space, they are enclosed in this level set of k squared plus 1 over u equals E. So I spare the detail, but it means that this function, when you sum all the Wigner function up to energy E, in phase space, you know what it looks like. It's a plateau function up to this level set, and it's almost 0 after that. And if you have this control, if you have this knowledge, then okay, this is in the Wigner function in the case of the harmonic oscillator. So this is the fundamental mode, n equals 1, 2, 5, 12. You sum the Wigner function here up to energy E, and you look at what it looks like. So if you first out this, you have ripples at the size of the difference of two energies, but if you first out this picture, what you have is something that will be almost a constant eigenfunction, and which decays after the k squared plus v equals E. You do that with disordered potential, like the continuous in 1D, like the speckled potential that I showed you before, and you do that with the landscape. It gives you, for instance, here, this is the original potential in 1D, the black one. The blue one is the effective potential. You look at the set k squared plus v equals E in phase space. So see here, you look in phase space, and here what is plotted in red in colors are the support of the Wigner function in the energy band around E. So what you see here is that if you do that with k squared plus v equals E, it corresponds, so it's very bad, You have a large number of very tiny wells that are not occupied at all, and even the shape is not good. If you do that with k squared plus 1 over u equals E, then here you can recognize that this, in fact, was this shape here, here, here. So you capture, what it says here is that, for example, if you were counting the eigenfunctions here, you would say, and you look this from the classical point of view, you would say there will be an eigenfunctions here because the energy here is much larger than the potential. So there is room for an eigenfunction. So that's what you would say classically. You can have a particle here. But in the quantum realm, it means that no, there cannot be a particle here because the well is too thin. And that's what the effective potential tells you here. The effective potential goes down here, but it doesn't go down by much. It says you cannot host an eigenfunction here. You don't have, because it has integrated, by computing HU equals 1, it has sort of integrated the fact that you have the connectivity, the wells, the width of the well is contained here. So here, this is a very bad prediction. This is much better. If you go to higher energy, it's the same. It's even more striking. And if you look at the plateau function, you sum all the eigenfunction, the Wigner function, up to energy E, and you compare with the level set k squared plus 1 over u equals E. You see that as you sum up the Wigner function of all eigenfunctions, you see that you have the prediction of the occupation of phase space. You have a very good control, in fact, where are your eigenfunctions in phase space. And if you have that, but you can use it. You can use it to make prediction, to make computation. And the type of computation that we have made, this is a work that we have done with Dominique Deland, is, for example, computing the spectral function. Spectral function is the decomposition on energy of, here it's for any state, but usually in Bose-Einstein condensate, it's the state of the cold atoms initially is a state of very low energy, so it's almost a plane wave around k equals 0. So you are interested for the computation of many quantities, you have to know the distribution in energy of a plane wave of momentum close to 0. So this is what is the spectral function. It's the distribution of energy of a state. Here are the predictions that are made for different values of eta, the quantity that I mentioned before. Here is the quantum regime, this is the semi-classical regime. In between, you have the transition. Here is the prediction in blue, the prediction with the localization landscape. In red is an exact computation, and in green is the semi-classical approach. So what it shows you that is, in fact, the localization landscape with 1 over u gives you a semi-classical approach, but with a new potential. It gives you the right zero order, where to start the semi-classical approach. If you start with V, you are doomed. You have to start with 1 over u. It's the right semi-classical approach. And then back to the mobility edge. So the mobility edge, now, it has a new... you can try to understand this in a new way. If you have what is the mobility edge? If you think that you understand where are the waves, but where are the basins, when do you have a mobility? When do you have something that delocalizes? When the basins, they start connecting to percolate throughout the domain. So a natural way of looking at the mobility edge is to ask the question, if now I look at 1 over u, I look at the basins of 1 over u, at which energy will this basin percolate? The region where 1 over u is smaller than E. So that's the question that we asked. We started from this. And here, so you have this Hamiltonian, you have the effective potential, and you look at the site where 1 over u is smaller than a given energy. And you change the energy. And as you change the energy, you have more and more sites. And you say, so this is sort of the classically allowed region, but in the language of 1 over u. And you look at that, and you look at when it percolates. So this is the result of numerical simulations with 1 over u, where 1 over u percolates for different values of the disorder. And this is what was known. So you put them one on top of each other, and you have this. So it means that all this branch here, you have two parts here. You have this branch here with relative low disorder strength. And the mobility edge here, in fact, it's simply a semi-classical object. It's the way where you when 1 over u starts percolating, it's where you have a classically allowed region. And when you reach a value of the disorder which is close to the maximum value of the kinetic energy, you are in a tight binding system. So the spectrum goes between -6 and +6, which means that the maximum kinetic energy that you can have in your system is about 12. When you have something which is a potential strength, disorder strength that is larger than the largest kinetic energy that you can have, then it supersedes everything, somehow, and you have this. But this part is a low disorder prediction that can be understood as a percolation of 1 over u. You can change also, these are computations that were done not for the uniform Anderson law, but for the Boolean binary disorder, the binary distribution. These are the prediction of 1 over u. So this branch here is a branch that can be understood semi-classically, and this is a branch that has to do with the maximum kinetic energy that is allowed in the system. And this is for continuous system, so for Bose-Einstein condensate. You have here the mobility age is for a continuous system. You have E equals 0.4, 0.45, 0.50. And here is the mobility age computed by Deland and Orso. This is the percolation threshold for the potential V, which is very low in the speckled potential. Very quickly, you have percolation. So it predicts nothing about the percolation, the mobility age. And here is the prediction with 1 over u. So it seems that we have something which is very close. The onset of delocalization of the mobility age seems to be related to the classically allowed region by the effective potential. Okay, this is, I won't have time to explain this because this is the new experiment by Alain that which we hope to have a very precise measurement of the mobility age because the previous measurements were quite crude. I'm sure that Robin knows about that. Just a word to say that there was even in a prediction by Anderson in his 58 paper, there was a prediction of the critical disorder at which you would have full localization. He was giving an upper bound of this critical disorder. And saying that, and it in the paper of Anderson, that's why later here it's And means Anderson, you have this equation in the paper, in page 10 of the paper. And in 2015, a mathematician proved that in fact this predicted upper bound was true, and it's actually an upper bound, but it took like, I don't know, 60 years to prove it. And even this upper bound, the actual value is 16, and the upper bound is 2 times 50, it's 100. So there is room to improvement. So I won't have time to show you that it can be applied to a semiconductor, disordered semiconductor, and that in this, just to tell you that it has been applied in disordered semiconductor, this localization landscape, and it gives computational gain by a factor of between 100 and 1,000 with respect to Schrödinger simulation. And just so I will skip the semiconductor part. And yeah, I have to mention this, otherwise Fabrice will kill me. So that we are doing localization landscape with hexagonal lattice and all sorts of triangular lattice. So these are all the conclusions that I hope that I've convinced you that this is a tool that has a lot of information and a lot of possibility. And so I will just conclude by this quote by Benaker, who made a comment on the localization landscape in the Journal Club for Condensed Matter Physics. So it says, to appreciate how astonishing this is, imagine someone telling you of a new method to find the eigenvalues of the large order matrix. I invert the matrix, sum the rows to obtain a column vector, then search for local minima in its reciprocal element. This sounds like a crazy method, but figure 2 shows it works for localized eigenstates. So it's basically it's where we are. Thank you.